So we have around almost 1.5 days to go through this Sweat Plus beginner workshop. So we will be starting today with the theoretical part. I will introduce you what is going on behind the scene within the Sweat model. Then Chris, who is our Sweat Plus, Sweat Plus plugin developer, and he will take you into the hands-on training on the Sweat Plus side. Okay. I will start with the theory part for the first hour. We are already a bit late, so I will try to cover it as soon as possible, Chris. Then after that, Chris will take over and we will jump into hands-on training. So we assume that you all have the QSwag Plus and other plugins downloaded and ready to use, right? If you have not, maybe meanwhile you can try to install a QSwag Plus plugin and a QGS and get ready to start as this takeover the workshop. Okay. I will start with my introduction. My name is Arun Baba. I am assistant professor with Texas A&M University and part of SWAT development team for last 5 years. And then we have Chris, who is our main developer on the GIS side. All those plugins you have seen previously for the ArcSwat, ArcSwat Pro, QGIS, QSwat Plus, and others also. So he has been working, I think, more than 3 decades. Yeah, more than 3 decades with the SWAT team, and you have the developer himself on the QSwat Plus side. So you will get very deep. You can take very deep dive into the QSwat Plus plugin with him. So he will try to explain as much as we can cover in this short video. Okay, so I'll start with the SWAT Plus introduction. Jacqueline, remind me when we have to take the break. Okay, coffee break. Yeah, remind me. Okay. And we have Jacqueline with us, and she's also our one of the software developer behind the scene for the SWAT Plus editor side or the other softwares we have for the SWAT Plus. All our websites, she manages everything on the software side and key resource to the SWAT team. And she is working with the SWAT team for last more than 2 decades. Jacqueline? Yeah. So that's good. But I'm relatively new to them, new to the team, so just 5 years. So I'm trying to contribute as much as possible. Okay. So let's start the fun part about the SWAT Plus theoretical part. So I will try to introduce you what is SWAT model. So how many of you have used SWAT previously? Any version of SWAT? No? SWAT 2012 or no? Okay, so everybody is new. Okay, so I have to explain in very deep. Okay, I'll try. Okay, so I will explain SWAT theoretical part, and then we will construct a model using the QSwat Plus for today. So for first and second, we will try to cover within today, and tomorrow we will run the SWAT Plus editor and visualization of the SWAT Plus output through the editor itself. Okay. Okay, so I will start with this story. So when I started with SWAT model, so SWAT stands for Soil and Water Analysis Tool. So when during my PhD I started using the SWAT tool, so I was introduced that it is a hydrological model. You can do water cycle simulations as well as you can get familiar with the water quality, or you can do the water quality simulation as well. But when I started using it, I realized it's not just a hydrological model. It is too big, too vast. There are so many processes. So during my PhD, I started taking it as not a hydrological model. It is an agro ecosystem model. But as I get more familiar with SWAT model itself, I got to know that it's much more than agro ecosystem model. So I'm calling these days that it is an ecosystem model. There are many applications, many ecological, economic scientists, and many other fields. They are using SWAT outputs and plugging it into their models and using it for the various applications. So SWAT itself, now I explain it as an ecosystem model. So these slides are a bit old, so we still have the same definition that it is a hydrological model, and you can do water quality simulations as well on that one. So other one is, so we are now at SWAT Plus, which is our latest version of the SWAT model. And with that one, you have the flexibility to go at any scale, any spatial scale. Like you can create a model for your particular field itself, just on a single location, or you can do entire country, entire basin, or entire globe. So you don't have any limit on the spatial scale. And then on the temporal scale side, SWAT, you mainly the classical SWAT used is that it runs on the daily scale. So you will provide your inputs, mainly the weather inputs, at a daily scale, but the outputs you can get at a daily scale, monthly scale, or annual scale. But the behind the scene in the classical model, it is running at the daily scale. So you are providing inputs at the daily scale. So there are options available if you want to do the sub-daily model also. That option is also available, but that is not many people use. So most of the applications are at daily scale, monthly scale, or annual scale. So you can do it that's temporal scale. So I will explain that how SWAT Plus has the different phases, like land phase, what is happening in your watershed on the upland side, and what happens when your watershed response, like hydrology or water quality, those components enter into the stream, and what happens into that one. So SWAT Plus has the capability of both to simulate the land phase as well as in stream phase. We call it water phase. So we will go into that one. So since you all are very new to SWAT Plus, you are getting introduced to SWAT. Let me tell you that SWAT is world's most used hydrological model. We have more than 7,500. So this slide is a little bit old, so it says 65, but we have more than 7,500 peer-reviewed applications, and it has been used more than 100 countries, and it has been used for many applications. Land cover, climate change, those are the most classical examples. But other than that, heavy metals, in-stream pesticide application, and these days people are using it for like emerging contaminant, PFAS, or mercury transport, or we are also developing for greenhouse gas emissions, carbon, how the carbon is getting stored. So that agriculture side also. So more than 100 countries, many applications, more than 7,500, and we have a large community of scientists which support SWAT. So it's not just us developers, like we are behind the scene of the SWAT model. No, it's the entire community. The people like you, they have been participating in the SWAT model development. So SWAT model is open source. The entire code, source code is available online to edit for free, and people, according to their local conditions, they are improving those codes, source code, and then they are submitting that source code to us. And then what we try to bring those, improve our model, those capabilities into our site. So it is under the continuous development. It's not just one time source code and we gave you. It's not. So every time on our GitHub website or others, you will see a new version coming up and a new version with the new capabilities. So we give the notes like what is improvements in this model. So it is under the continuous development. And other thing is the one why SWAT is most popular, but we have tried to make it as user friendly as we can. Okay. Because the people like we have Chris, Jacqueline, and James, they don't have that background like agricultural biology or modeling background. But because of them, they are the software developers. Because of them, they are developing these tools for us so that we create a very user-friendly software tools. And based on the needs, every day somebody approaching us, okay, I need this one. Can you incorporate that into tools? So if that is easy and that is more general use, we try to incorporate it in our models and take it to a next step. So the entire team is working towards making you a good experience, making it as friendly as possible. And all these sports, you can just go to the SWAT website, and there is a sport tab, and just there are many ways you can connect us. I will show you later on. We are trying to resolve the issues you guys are facing every day. So feel free to reach out to us if you face any problem at any moment. So as I mentioned, so SWAT is not developed by a single person. It has a very rich history. More than it's not just the contribution of the modelers. It is also all those field scientists. They collected data in those fields that helped us to figure out what is physics going on behind each process, to convert those into the physical equations, and then bringing those into the models. So SWAT Plus itself has, since the model development part, has more than 45 years of history. So as I mentioned, like this one is under the continuous development. So for the last 45 years, we are trying to improve each process step by step. And so I'm saying like you can trust it. You can put your trust into this one. Each process has been gone through a lot of scientific proofing or scientific knowledge, and it has been applied for more than 100 countries. So you guys can trust what the process is going on behind the scene if it is a generalized case. And then for your special case, you can easily modify it to make it more suitable for your local condition. Okay. Okay, so as I mentioned, so we simulate both land phase processes as well as water phase. Land phase, what is happening in the upland side of your watershed, and then when it enters to your stream, what is happening within the stream. So we will dive into that one in the later on slides. So the main driver in the SWAT model, the main driver of all the simulation is the climate. Why climate? So in the SWAT model, we have four main inputs: topography, that is topography, land cover, and soil. So if you see these three inputs, they are relatively stable, static. They are not changing that much with the time. But climate is the main dynamic variable which is changing every day. Okay, so you will set up your model with the land cover, soil, and topography. So as everything model is set up, so our main dynamic variable, the main controlling variable would be the climate. So all the processes will be controlled how the climate behave, and these three how they affect that dynamic variable. So that's why our main driver would be climate. In the land phase processes, as I mentioned, that upland watershed part. So on the upland in your watershed, in a particular land cover, how the hydrology, what would be the entire water cycle for that? If some rainfall or precipitation is coming, what would be the fate of that precipitation? And then how that would affect your plant growth at that location, your land cover, then how much it can take that water with the surface runoff, how much it can take, soil with itself, what is the potential of soil erosion, or nutrients you are using on that land cover. So all those processes comes under the land phase processes, and that will be simulated. And then SWAT plus, after simulating that one, SWAT will bring those into the in-stream, and then the in-stream water phase process would start. That, for example, from one point to second point, so you have a water velocity, you have a slope in the stream and everything, and then sediment particles, they can settle down, right? They are not going, okay, dissolved material from one location to second location, they will reach, but the sediment, what would happen during that in-stream from one location to second location? What would be the fate of the sediments? How much they would settling would happen? Or if there is bank erosion from the stream side, how much that would be? So all those processes would come under the water phase processes. Okay. So let's talk about climate. So in SWAT, you can provide 5 inputs: precipitation, minimum and maximum temperature, relative humidity, solar radiation, and wind flow. So you have to provide this one at the daily scale. Even you want your outputs at monthly scale, annual scale, but SWAT itself has to run at the daily scale. You can visualize your inputs, outputs at monthly scale. It will combine or aggregate all the responses and give you the output, whatever you need, but it has to run at the daily scale. Okay, so you have to provide all these. And precipitation and temperature, these are the required. You can skip relative humidity, solar radiation, and wind speed, but you have to provide precipitation and temperature because these are the main drivers to control the entire watershed ecosystem. Okay. Why we need this one? It depends on. Are you guys familiar? So when I'm doing this presentation, I am assuming that you guys are familiar with the basic concepts of hydrology, like what is surface runoff, what is infiltration, what is evapotranspiration, and all those, right? Potential. Okay, so if you don't have, talk with me during the breaks, and I will explain you in details. So in SWAT, we have 3 different methods to calculate the potential evapotranspiration. One is Penman-Mondiat equation, that is more complicated. So if you want to use that equation, so you need to provide all these 5 variables. But if you don't have the inputs from these 3 variables, you can use the other 2 methods, Parsley-Taylor or Hartley methods. So that's how the things change. So you can provide 5 climate inputs, and 2 of those, precipitation and temperature, are required. And then, yes, we prefer that you guys provide us in the SWAT model, you provide the observed data. Observed data means like locally collected, weather station data, or you can utilize the satellite product. There are many satellite product, climate products. You can utilize those ones. We do provide you the weather generator, so that stores the statistical information about the weather at your location. But we ask you to provide the observed data and utilize this weather generator only to fill up the gaps. If there is any missing gaps, or if you have like precipitation and temperature, but you are missing all these 3, so then weather generator will, as per your location, it will bring those 3 variables also. Okay, so weather generator will provide the plugin. I think when you were watching that video by Jacqueline, downloading the Q factor, so there was one option to pick that. Do you want to install the weather generator or not? So that was for this one. Okay, yeah. So precipitation is classified as rainfall and snow. So depending on temperature on that particular day, the form of precipitation would be decided by the sweat, whether it is a snow or whether it is a rainfall. And rainfall is like the liquid, and snow is the solid part. And based on the temperature on that day or some other variables, when that snow will be melted or will that snow will be accumulated. So all these things are happening. So precipitation is there in two forms, both rainfall as well as snow. Okay. So SWAT is semi-distributed model. What does that mean? That what it do, like based on your location, your interest, your watershed area, your region of interest. So what it will do, it will divide that watershed into smaller units. The good thing about SWAT is that you can control its complexity. You can have it as detailed as if you want, like depending on your computational power. If you have a strong computer, you can do a lot of computation. You have good amount of time, right? So you can go as detailed as you want. Also depends on your objective, but you can also make little bit coarser objects in the SWAT. We will explain this when you will delineate the watershed. You will see how we divide the watershed. So in the SWAT, so first watershed is divided into smaller units, landscape units. Okay, then those landscape units are further divided into HRU, hydrologic response unit. And I will be using this term HRU, LSU a lot. Okay, and this will be also using this term. So what HRU is, let me explain HRU in the next slide. So the key takeaway from this slide is that how we distribute SWAT model, and then all the processes which we cover under the land phase processes, like the upland side, all those hydrology, sediment, plant growth, that everything would be calculated at small scale, HRU scale, and then aggregated into LSU scale, and then aggregated into the watershed scale. So you will get your outputs. You can get your output at HRU scale, you can get your output at LSU scale, and you can get the entire watershed picture also. Okay, so it's a semi-distributed model. So as I mentioned, that you can divide your watershed as much as you complexity you want, and because of the competition is happening at the HRU scale, so you can control number of HRUs in your watershed based on your computational power, and we will see that one later on. So I mentioned we use three inputs: soil, land cover, and topography. Okay. So HRU is a unique combination of these three. Like for example, if I on this HRU I have corn, and I have loamy soil, and I have slope of 0 to 2%. So this is my one HRU. And any of these three property, if I change even one, let's say this is adjacent field, this one has corn, same soil, loamy soil, but the slope is different, 2 to 8. So these are the two different HRUs. Okay. So HRUs are like based on these three combinations, a combination of these three properties, a unique combination of these three properties, we call it HRU. Sorry. So HRU is our computational unit, and you can see from this like Lego set. We assume that you played with the Lego set. So when you have this entire, me go to the pointer. Okay, right. So you can. So when you have the entire thing set up, so this one looks like a watershed, but HRU is all these small unit you have in the Lego set, and the calculations are happening at those each location, and then aggregated into the watershed scale. Chris will explain HRUs more in detail when we delineate. So that's why I'm skipping more discussion onto this one. So on the HRU, we will calculate all that hydrology, erosion, plant growth, nutrient cycle, pesticide dynamics, agriculture management, everything would happen at the HRU scale and then aggregated into your spatial scale, your interest. So each HRU has it's even a 1D object. So we have divided into multiple layers. First is what would happen depending on your climate, how much precipitation is coming. And out of that, based on your soil properties, land cover properties, topography, it will divide that coming precipitation into infiltration, surface runoff, and based on your temperature, how much would go to the evaporation, how much would go to the transpiration, and then the water which is entered as infiltration, what would be the fate of that? Some of it would go to the lateral flow, some would percolate into the deeper soil zones and into the shallow aquifer or your deep aquifer. So those kind of things are there in SWAT for the hydrology perspective. So we are simulating the entire water cycle and each of these processes. Yep. So as I mentioned, that everything is happening at daily scale and at HRU scale, then aggregated into your next scale. This is the same, that everything is happening at HRU scale, and then we are going for the, okay. So yeah, this is a little bit something of interest. Like I receive a lot of questions on this one, that are these HRUs, like you divided your watershed into small HRUs, are these HRU talking with each other, or are they contributing to? So as I mentioned, like SWAT has been product of over 40 years and more than 100 countries use. So we have some simplification and some complications into the model. One of the simplification is that if you don't need HRU routing, then it will not have the HRU routing. So for example, HRU1 would be talking directly to the stream. So whatever response here is generated, that would directly contribute into the in-stream. And HRU2 would contribute into stream. So it is not going like that. HRU1 is contributing to HRU2 and then going to the stream. So it is not like that. It may sound to you like, okay, this is not the real world thing. It should be the other way, that HRU should talk with each other. But as per calculation, so as per our simulation over the years, and the other way, like a simplified way, has been working very efficiently for most of the applications in the hydrology world. But with the SWAT Plus, we have made some improvements. You can route your HRU too, if you want, okay? But not necessary. So, yeah. Sorry. Okay. So some of the water cycle components. So as I mentioned, we for the moisture inputs, you have the precipitation, which is in form of rainfall or snow based on the temperature of that day. Then other inputs could be like snow is accumulated and that is getting melted, snow melt. Then irrigation, if you are using some outside source, maybe from the deep aquifer or maybe some your local source, somewhere else, like not from that particular HRU. So these are your hydrological moisture inputs into the model. Okay, and then first thing is potential evapotranspiration. So there are three methods, as I mentioned, to estimate potentiality: Hargreaves, Partley-Taylor, and Penn-Montiac. So Penn-Montiac is the method where you need all those 5 inputs. If you don't have, locally observed inputs, we ask you to use partially tailored or Hargrave methods. And there is no golden rules that which method you should use among those. It depends on your location. Both methods have their own strength and limitation. So based on your location, you can choose any of those. Okay. So SWAT simulate evapotranspiration, like it is simulating evaporation as well as transpiration. Transpiration is based on that how much plant growth is happening and what is the potential, what is the soil water available for the plant to utilize the water and transpire into the environment. And then in the soil moisture, in how much soil moisture is available for directly evaporation. So both are calculated and summed up into the evapotranspiration. So for the surface runoff, when you are using the model at daily scale, we use curve number method. I'm not taking you into the curve number method, but it is like each land cover would be assigned a number based on its land cover, like land cover, soil, and management. All these three. Like, for example, your surface is pervious or impervious, right? Is it agricultural land or urban land? So urban land has the more potential to surface runoff than the agricultural land. So urban land would have the higher curve number than the agricultural land. And then among the agricultural land, so what is the soil conditions? Okay, if your soil is more clay soil, like it or it can have hold the more water, then it has a different curve number than a sandy soil, which can hold less water, right? So all these combination of land cover and soil. So you don't need to do all these things. You just provide your soil properties, your land cover properties, and everything else is done within the SWAT. So it will assign based on your properties a curve number to each location and calculate the surface runoff. Okay. So SWAT use the curve number method when it is a daily scale, but it use green and amp infiltration method when you are using a sub daily scale. Okay. So when you are using a daily scale, so what it will do, your precipitation is there and it will calculate surface runoff out of that using curve number method and subtract these two to calculate infiltration at the daily scale. But when you are using sub daily scale, it will calculate based on the Green-Amp equation, the second equation. It will calculate what is potential of your soil to conduct for the soil hydraulic conductivity based on that, how much it can infiltrate, and based on that limit, it will calculate what would be the surface runoff, precipitation minus infiltration capacity, and then it will calculate the surface runoff. So two different methods at two different scales. If you want, so we have SWAT theoretical document available on our SWAT website, and all these methods are explained in very detail on that one. Okay. After that, after infiltration, what would be the fate of the water as it infiltrates into the soil based on your soil properties, how much it can hold water into it, and if the water is more than soil water holding capacity, or we call it field capacity of the soil, then it will start flowing, right? If there is, depending on the slope of your HIU, so it can flow laterally, or it will go deeper into shallow aquifer, percolate below the root zone, and it will percolate to the shallow aquifer or the deep aquifer. And then depending on where you are, depending on the lateral flow, and it may enter back to stream or may go into the shallow aquifer or this. So when we will be calculating the water yield means the stream flow into your stream. Then it would be a combination of surface runoff, lateral flow, as well as return flow from the shallow aquifers. Okay, so it would be combination of all three. Yeah, so this one is like after the lateral flow, how much you can percolate, how much there is potential for the return flow to the stream itself. Then we do have capillary reactions also, right? Depending on your soil, and there is always potential for the capillary rise, the water rise to the capillaries and used by the plant roots, okay, for the transpiration. So we do have those factors also, and you can control that into a SWAT model. Maybe we will talk about that later on. So this is entire hydrological cycle, water cycle, how the sweat is simulated in the sweat zone. Okay. And yeah, percolated water into shallow aquifer or deep aquifer. So key takeaways like sweat runs at a daily time step in the classical. Outputs you can generate daily, monthly, annual. And there are two types of processes, land phase and water processes. What we will talk about that later on. And watershed can be divided into smaller structures, landscape unit, and HRUs. And HRUs are the smallest unit to do the entire calculation, to do all the simulations. So any question up to here? Okay. Thank you. Okay, let's dig deep dive into plant growth and land phase processes. So there are many other hydrological models also that this plant growth phase, but that evapotranspiration is usually the biggest component of the water cycle, right? It varies from 60 to 90% depending on your location or arid, semi-arid or humid conditions. So it is the biggest component. So, and that component is entirely controlled by the plant, right? So in SWAT, we have a database of more than 200 plants, 200 different plant species like corn, cotton, wheat. So each of that land cover has some parameters like how much water it requires, how much solar radiation it requires, how much biomass, how many days it takes to reach to its maturity stage. So all kind of those plant parameters are there. They control this entire plant growth process. You can edit those databases also. We will see that one later on. So you can control the entire plant growth by yourself also based on your local conditions. So how SWAT grow the plant? So as I mentioned, so we have this database. In that database, I know for my corn, if I give it optimal condition, like solar, it know how much solar radiation is reaching to me based on your climate data. And then it know on that particular day what is my leaf area index, like how much my plant has been grown on that day, and how much solar radiation I can use efficiently based on the leaf area index. Okay. After that, it knows that under these conditions, how much I can grow in one day. That is what we call it optimal growth. Okay. But the conditions are not optimal. The conditions are not ideal in the world, right? So maybe you don't have enough water to support the plant growth. To reach to this optimal growth, you don't have enough water. Maybe you don't have enough nutrients. Okay, the temperature is too high. It is damaging your plant, right? Or the condition in soil condition, those are anaerobic condition, and plant don't have aerobic condition for the root growth. So SWAT calculates these stresses, all of these individually based on like on that day my corn plant need this much water, but soil water is only available this much. So it calculates what is the stress. Okay. And after calculating these stresses, and then based on these stresses, it controls. I will not go to the optimal growth. I will go to this particular growth only. Like if I can reach, I can grow 1 gram per day or 1 kg per day, but my stresses are 20%. So I will grow only 80%, not the 100% potential. Okay. So that's all the stresses are calculated in the SWAT model. Okay, and you can grow multiple plants into one small HRU. So because HRU is the smallest unit of the computational, you can grow one like corn, or you can do the multiple crops also. But we are working on that one, not yet efficient. And then after plant grow, the entire production, the entire response is then divided into different units, like how much go into the seeds, how much biomass, how much root biomass. So for all these processes, we have separate equations. You have separate equation for root growth, separate equation for biomass growth, and how much biomass is converted into the your grain yield and others. So all those equations are there. Okay. Okay. And then so based on the plant growth on that each day, then it calculate evapotranspiration and other processes also that control the rest of the hydrological cycle. Okay. Then we have the water quality components also. Erosion first is, so we used modified universal soil loss equation for the SWAT. So as you know, that based on your so erosion depends on many factors also, like what is your soil type? Is it more sandy or more clay? And so it will calculate based on that these factors, like soil erodibility factor, depending on your soil composition, and then depending on what kind of land cover is there and how you are managing that land cover. So all those management factors, do you have cover crop? Do you have corn? Or are you tilling your field? Or it is under conventional till, it is under the conservation tillage. So those kind of management factors. So all these factors are considered to calculate the erosion, and then utilize the modified universal loss equation to calculate erosion. Okay, and we are currently working on improving our soil erosion model into more, you can say, more logical, more real world, to represent more real world. So we are working, but as for now, we are using modified Russell equation, and it has been working, and we could. So unlike the other models, they utilize a very basic nutrient cycling model. SWAT has a very detailed nutrient cycle model modules. So this one is for the nitrogen cycle. So inputs, you have fertilizer, the commercial fertilizer you put into your field, you can use that one. You have organic fertilizers like manure or other waste, cow manure or dairy manure or other manures you can bring over, or the sludge from the treatment plants. And then other, like there is atmospheric nitrogen deposition also, because nitrogen is abundant in the atmosphere. That is also. Then you have some of the legume crops you can use, that also utilizing atmospheric nitrogen to dump that into the soil. So all these inputs are there, different kinds of inputs you can give it to the SWAT, and then SWAT take those inputs and simulate the entire nitrogen cycle. That how much would go under the immobilization or back to the mineralization, then how much we will go, how much nitrogen will go under the nitrification. Okay, and you can control. There are different methods of applying fertilizer also, like you can spread it, or you can input it with the liquid, like with the irrigation. And there are, I think, more than 40 different kinds of fertilizers available in the database. You don't need to change, like all those most famous fertilizers like urea, 4600, 15, 15, 15, nitrogen, phosphorus, potassium, or cow manure, dairy manure, hog farm manure, uh, poultry farm manure. So those kind of database are already available into the SWAT model. So you don't need to, you just have to mention like what fertilizer you are using, and rest would be carried out. This is, and then we do have denitrification process also based on your aerobic or anaerobic conditions. So entire denitrification would also happen, and then greenhouse gas losses. Okay. So it's not just the hydrological model, it has entire plant growth module, it has nutrient module, and it has greenhouse gas modules as well. Okay. Similar to nitrogen, we have the phosphorus cycle also. In the phosphorus, we don't have atmospheric deposition or those things, but we have the fertilizer, commercial fertilizer based or through the manures, and that goes under mineralization or other processes. And then phosphorus is less susceptible to loss through runoff, so it can get absorbed by the soil heavy metals, and then it can move with the soil erosion, right? As soil will get eroded, so phosphorus will also get. So it has both, like nitrogen and phosphorus, it has both dissolved forms, inorganic forms, and the undissolved or other forms like that get stick with the soil particles or others and can go with your runoff and reach to your water channels. Similarly, we have pesticides also. People are using, so in the, like depending upon your plant growth at that time, you will apply the pesticide, and based on the leaf area index, it will intercept like how much would be utilized by the plant and how much would be directly get applied to the soil surface, and based on the soil surface, how much, what would be the further fate, how much would go to the surface runoff, how much will enter to the infiltration and wash off. So those things. Okay, so this one, this thing we will do in the SWAT on the second day tomorrow. A simple example of land management. So when you are setting up your SWAT model, you can specify all these land management. For each hectare, you can define what is your crop rotation. Is it corn every year? Corn, soybean rotation, corn, soybean wheat rotation, corn, then cover crop during the dormant periods or like fallow periods, and then soybean. So all kinds of crop rotations are possible. And then how much biomass you want to remove, how much you want to remain there. Do you want to remove it, or you just want it to be like used as residue for the next cycle, like cover crop? You don't need to remove the entire biomass, you just use it residue. Then you can define what kind of tillage, like many people use it for the environmental science, like what would be the effect of different tillage on soil erosion or other soil properties, soil carbon stocking and all that. Then different kind of fertilizer and different kind of fertilizer type as well as application methods. Then do you want to graze? And all those animal operations are also there. Then different kind of pesticides, not just agriculture, we do have for the urban management, forest management. You want to do prescribed burning, what is the fate of nutrients after the prescribed burning of fire, of that. So all those things are available for you to do. Okay, irrigation, conservation practices. You want to include wetlands somewhere. You want to control the soil erosion with the different practices. You want to create a terrace or others. So all those things are available in the SWAT land management. Okay, so key takeaways from the land processes that you have entire plant growth module and you can control it based on your objective. You can go as much as detail you want, or you can let it SWAT use itself from its database from that knowledge we have developed for last 3 decades, and you don't change it, but it depends on your objective of your study, how much you want to control it. Okay. And then there is land management, how accurate you want your agriculture management or forest management or urban management to be represented into the SWOT model. Okay. So all these things are you can do into the SWOT model along with just delineating the model. Then comes to the in-stream processes, like after the land phase model, everything is entering to the stream. Now the processes would happen in the stream itself. So first thing, SWOT is hydrology model, not hydraulic model. So don't expect that we have very detailed hydraulic component. So there are a lot of assumptions and simplification when it comes to the in-stream process. We do have those soil erosion, but like for example, you use some pesticide, some chemical, right? And that chemical enter to the in-stream. Each chemical has their life, like it will decay half after this many days. So those kind of things. So those all will happen within the instinct. But the simplification is that if it is dissolved, for example, nitrate, if it is dissolved in the stream, so I assume that it is well mixed layer. Okay, so the entire water layer is well mixed. So there is no different layers into the instinct. So those are the simplifications from the hydrology point of view. That's how we need it. That's where most of the applications are. But we don't like complicate the things into that one. Okay, as I said, like so it assumed that your channel is trapezoidal phase. Okay, and based on your topographic information that you provide as this digital elevation model, and it will calculate channel length, channel width, channel flow, as well as the channel dimensions. Okay, and then it will assume it as a trapezoidal and well mixed trapezoidal channel cross section. Okay. Then we have different routing methods. Two of those methods, variable storage and Muskingum. And again, there is no golden rule that which method you want to use out of those routing methods for the same routing. It depends on your location, but most of the time, default is variable storage, and that works. You don't need to. If you want to simulate some in-stream processes and you want to see that how those different methods can control your, then you can do it. But there is no particular golden rule that in which condition, which one to use. So as I mentioned, that it is a well mixed water layer. If there is anything which is dissolved, so it will be dissolved very well. So it will at each your spatial scale, the water will come in and then get out of that sub-basin or landscape unit out of that, okay, from that water channels. Okay, then we do have some of those structures based on the demands. We have been working a lot toward that part, especially on the reservoir management. So again, on the reservoir, there are some processes are very detailed in very detailed manner, but there are some processes which are not that detailed. For example, its reservoir is again a well mixed system, so we don't have those layers, but you can control the reservoirs in many ways. So you can have, so if I define reservoir, it means like it is a big water structure on your water channel. It's big water structure on your water channel, and that will have multiple inflows. The water is controlled, and then it has outflow. So in Swattler, you can have many inflows to a reservoir, but only one outflow to the next channel, because it is connected to a channel, so it will only have one outflow. But definitely, it's not that you can still distribute the water in many ways. Like you can define your withdrawals, how much water out of that reservoir you want to use for the domestic application in your city. So Stratus gives you that flexibility that each of this subject you can distribute your response. That whatever input into the reservoir, 60% is going this way, 40% going this way, that way. Then we have a concept of decision tables. That is a lot of if else scenario. If my this year is not under drought, right? So I will have more discharge. If I am facing a drought condition, then I will have less discharge from the reservoir. So we have that decision table concept you can utilize to control your reservoirs into very detailed, but that is a topic of advanced workshop. So we will not cover in the beginner workshop, but those things are there that you can control the water structure into very well mannered. Like same as in the fertilizer application also. Like sometimes you want to automate some process, irrigation. You don't want to put a particular irrigation. You say if my soil has the soil moisture less than this value on a particular day, then irrigate. Then irrigate with this amount. If else if my soil water condition is this, then irrigate it with this one. So you can put as much as conditions with those decision tables. So you can control each of these water structure or any object in the SWAT plus in very detail. So this is the reservoirs. It can have many inflows, one outflows. Again, the same way, well mixed system and sorry, yeah. Then we have ponds. The difference between pond and reservoir is that it don't have a outflow, and the pond could be anywhere in your watershed. So reservoir is mainly on the main channels, so it gets storage. But pond, depending on your topography, visualization model, or you may want to define that is not captured by your DEM, you can define by yourself where that pond is. Rest is similar to the reservoir. Okay, so from the water processes, key takeaways are that there are instant processes, but those are simplified processes. Those are available there from the hydrological perspective, not hydraulic perspective. Okay. Yeah, we discussed this one. And then, so this question is usually I ask like, what is the difference between a pond and a wetland? Anybody? Do you know about wetlands? No? Okay. So, so pond can also collect some water and wetlands also can collect some water, but wetlands have some plants into it. So usually wetlands is one of the management practice very widely used to control the water quality. So if you are on a small channel, if your water is coming and it is carrying a lot of nutrients, and then it can enter to the wetland. So wetland slow out the flow process. It gives time for those plants to utilize those nutrients, and the outflow from those wetlands into further would be better in water quality. Like nutrient is used by the wetlands, and now you will not have that nitrogen and phosphorus to cause your problems like eutrophication or others. So wetland is one of those. So wetland has, the answer to this question is wetland has plants and not that one. So as we are discussing that SWAT strength, that it has a lot of strengths, that you can make it as detailed as you want. You can make it as computational efficient you want, like compromising on that detail. You can define each of those inputs, each of that land-based processes. You can control it. Literally, you can control each of the process. Even if you don't want to control it, if you use our default value, it will still give you acceptable response. Why I'm saying that? Because I use SWAT a lot. So when so there are two source of error when you are developing a SWAT model. So first source of error is your input data. So if you have better quality of data, you will get better results, right? Well-defined topography, well-defined land covers, well-defined soil, better response. If you don't have good quality, so that is error of source. Second is our parameters in SWAT plus or in SWAT model. So there are a lot of parameters which are based on general conditions, but they are still there from our knowledge of last more than 3 decades, right? People are using more than 100 countries. They still work, but they still need to tweak a little bit for your local conditions. Okay. So, so the strength is that if you provided good quality of data at annual scale, you can still trust those responses. But as you go finer scales, so you need to tweak some of the input parameters to get better results. But overall, that you guys got a, I think, test that how complex all those processes are, how detailed those processes are in the SWAT itself to calculate those responses. So it is very comprehensive model, and then it has entire land phase process, plant, and everything is calculated. Nutrient cycle is calculated. It's not just a hydrologic model. Okay. Then in the channel process, so there are many inputs and outputs you can control. Irrigation point of view or nutrient application point of view, you can control from the land use management point of view. A weakness is it is comprehensive model, very detailed, but computationally expensive, right? So data demanding. If you have more and more information, you can put more and more information. Okay, so data demanding as much as you can, you can bring it. Calibration that I mentioned, that based on your local condition, if you want to capture those local conditions, you have to tweak some of those parameters little bit up and down, so you capture your local condition. So that's the process we call calibration. Okay, otherwise you can still trust those responses at annual scale or larger, like for the global studies, right? If you want to do a global study, so you don't need to tweak the parameters for each location. You can to get a bigger picture, you can still trust it. Many of the processes we have already incorporated in the SWAT model, but some of the processes are not that simple. Like if you want to simulate the glaciers or others, and those are very complicated methods. They are there, but if you need, you have to get more in depth into the SWAT model. So that is one of the weakness. Like they are not that user friendly as of now. So yeah. Another one is that it is popular. Many people are using it, more than 7,500, a lot of users. But I have seen like people use it in any way, like just to get their response. They can do anything. So use only the trusted source, especially if you go to our SWAT website. We also provide the literature related to SWAT, and those literature are selected by our team, like which we don't want to share any low quality journals publications. we all share only the good quality journal. So everything is available on the Square website. So if you have any particular topic of interest, select it, sediment, and you will get a lot of it. So we ask you not to use those misleading information. You can get your right answer for many wrong reasons. So don't do that when you are using it. And so, as I mentioned, like many processes based on from the hydrology perspective, yes, those are detailed, but from other application perspective, those are not that much detailed. Okay, like the in-stream processes. So, though that is one of the weakness. Okay, so I will leave you today with this my last slide today. So we have mainly 4 inputs. You provide land cover, topography, and soil information at a watershed scale. All these are static. So as you provide it, so it is stable there in your model. Then you provide a dynamic variable weather, and that control entire hydrology and outputs. And you can get that at daily, monthly, yearly scale, or also like over the long period, average annual statistics. And along with that inputs, you can control a lot of processes with the land management, irrigation, fertilizer, and other processes to get those. Okay, so any question? Yes.
I didn't ask what your people say about the calculating number. Yeah, I don't know what's self-daily scale.
What is?
Self-daily scale.
Okay, sub-daily scale is when I'm saying sub-daily scale, like sometimes you need outputs at hourly scale. Right? For example, I am developing a flood warning system as of now. So to develop that flood warning system for example, this city, I need to get hourly scale precipitation of 15-minute precipitation and then generate outputs at 15 minutes or hourly scale. Okay, these are some daily scales. Okay,
It says hourly.
hourly scale or 15-minute or like twice a day. So it depends on like the resolution of your data. So you can do that sub-daily scale. So we prefer hourly scale.
Okay, so again, the data can be the input data.
Yeah, input data can be at hourly scale, but the method will change. Like if you are using hourly scale inputs, weather inputs, so you will use green equation to govern the hydrology, not the current number. So current number is used when it is daily scale. So green equation depends on hydraulic conductivity of your soil, and so you have the hourly scale precipitation inputs, and you have hourly scale hydraulic conductivity. So it calculates how much water can be infiltrated, and the rest would go to the surface. But that is not possible at daily scale. So that's why we use current number. Good question. Thank you. Yes.
What's the size of each one?
What's the size of HLU? So,
I think we'll answer it later.
yeah, okay.
I'll answer that later.
Yeah, okay. So Chris will answer you that one later in his slides. Yeah, we will go to delineation in very detail. So a lot of questions would be answered at that time. Okay, so any question? Do you want to take 5 minutes?
The schedule says half an hour. The schedule says half an hour.
Yeah, half an hour. Okay. You can jump on. You want to use your laptop? Yeah, I will be here all around the entire day, so ask me if you have any question.
So you're having a break?
No, you people listen to the content.
Okay. We might give people 5 minutes.
Yeah, take 5 minutes if you want to use the restroom or drink the water while this is set. I will stop my screen share and Christine will start the screen share from there. We'll be back in 5 minutes. Online participants. If online participants has any question, please type it in the chat and I will try to answer it. Thank you. Right.